So thanks, Francisco, for the introduction. So I'm going to present some work I did really a while back, 2013, 14, on the Planck results. And I want to use this as part of this conference as a cautionary tale about extending knowledge gain from a limited category of object to a much broader range. Here, of course, it's in the traditional pre-machine learning, pre-artificial intelligence data processing era in astronomy, given the date, but I still believe this is valid. So for those who've never heard of the Sunyaev-Zeldovich effect, it's basically a shift in the CMB spectrum. It's equivalent to a shift in temperature. What happens is the CMB photons, when they go across clusters, they get upscattered in energy by the electrons of the hot gas, and it is equivalent to changing the temperature of the CMB by an amount which is proportional to the integral over the line of sight of the pressure in electrons in the gas, as shown by the equation on the right. So given that it was 2013, 2014, I used a simulation we ran with Ian McCarthy, who was my PhD supervisors during my PhD. They were called COSMO, overwhelmingly large simulation, or COSMOS for short. It's a really large set, which is why it's, I believe, to the best of my knowledge, it's still the largest set of cosmological hydrodynamical simulation that vary subgrid modeling in large boxes. The subgrid modeling is that is varied is basically the metal-dependent radiative cooling, thermodynamic and stellar evolution, star formation, kinetic supernova feedback, AGN feedback. You have all the references here, and the references to the papers at the top are clickable links in case you're interested to learn more. And given that it's a large box, it has a really large set, and we've been able to show at the time in that paper listed at the top that they were producing realistic populations and groups and clusters, and thus we can use them to try to understand or interpret observations. So back at the end of 2012, we were baffled by that Planck result that came out that displayed as a science point on the plot on the right, which seemed to show that the SZ flux as a function of halo mass is a self-similar scaling relation all the way from galaxies to clusters, or the other way around as you prefer. And it's extremely surprising because that's been ruled out by X-ray observation for the past 30 plus years. But Y500, there's a Z-flux within R500 is not actually what is directly measured by Planck. So if you want to try to understand what kind of systematics that they haven't already tested could be causing this, you need synthetic SZ observations. And that's exactly what I did. I developed a Lycon software. I used it to make Lycons that were 5 degrees on the side. 5 degrees basically 400 megaparsec per inch at redshift 3 in a Planck of W7 cosmology. Lycons, so they were going all the way back to redshift 3. So you have the SZ background properly, at least a large part of it. And we also made a synthetic catalog of halos that's analogous to the halos that were supposed to host the Planck locally brightest galaxy sample that was extracted from the SDSS-DR7. So we took all halos with redshift less than 0.4 and masses above 10 to the 12. I had to use DOMAP7 simulations and not the Planck ones in terms of cosmology, but it doesn't matter, it doesn't change the results. Because that was the only set for which we had 100 megaparsec boxes with higher resolution that allowed us to go all the way down to galaxies while still having resolved halos. So here is what it looks like in terms of a 5 degree by 5 degree wide map. And what you do is you contact someone in the Planck collaboration, namely Jean-Baptiste Melin, who wrote the match filter that was used on the Planck data, and was of course part of the Planck team. And he kindly agreed to take the catalog and the maps and redo exactly what they did with the Planck analysis. So stacking the SD signal around all the halos in bins of mass and measuring what comes out of the match filter. So here I want you to focus on the black lines and symbols. The lines are the true 3D signal that measured directly in the simulation for those halos. And the black symbols are what you recover using the match filter on the maps. And what you find is that if you, in a non-radiative model, basically no cool, you do not allow the gas to cool, which would give you a self-similar scaling, you recover pretty much what you put in. So it's good. But as soon as you start adding physics, and especially as you increase the intensity of the AGN feedback up to a level where you start getting a realistic population, for instance, with this AGN 8.0 model that I'm showing here, it's the best model in terms of fit to a lot of data, especially for the gas and also the galaxies. And you find that the amplitude of the bias is increasing not only with the intensity of the feedback, but also with decreasing mass. And it's nearly an order of magnitude at the lowest halo masses. So what could be going on? One assumption that's being made in this filter is that the pressure profile is self-similar, is the same everywhere, and it's self-similar in terms of its evolution with the mass, once we scale in the proper units, and it's the same over the whole radial range, and it's basically what was found by Arnaud et al. 2010 by fitting clusters observed in X-ray with XMM and non-radiative simulations. And if you start looking in realistic simulation and you bin the things in mass bin all the way from galaxies to clusters, you see that's not what you see. The black points are the measurements in the simulation. The blue is the Arnaud filter, and it's basically a generalized NFW shape. And if you want something, while keeping the generalized NFW shape, that works for the whole radial range and the ball mass range, you need to make two of those coefficient mass dependent, which they weren't at the time, and that you obtain the red line. And if you substitute the blue line by the red line in the filter, you get this for this AGN model. So you've largely removed the bias. So it means large part of the bias was due to this inappropriate spatial filter, but there is something that's left. And in fact, Planck does not measure Y500, it measures Y5R500 because it doesn't have enough spatial resolution to resolve Y500. So they use a conversion factor to go from the signals they measure, which is Y5R500, to Y500, and that conversion factor is always the same, and it's computed for this best fit analytical profile. And given that this profile is not what we have in the simulation, even if we use our best fit profile, compute the conversion factor, there are still things that remains. So what if we were to look directly at what Planck measures? That's what we did here. And what you find is that you still have a small level of bias, but by not using this conversion factor and improving the shape of the spatial profile in the filter, you manage to make it relatively low. You have now, if you focus on the plot on the right, good agreement between the model that contains the AGN and the Planck data in cyan, whereas on the initial plot, it was agreeing with the non-radiative universe, which is now ruled out by this like-with-like comparison. And I mentioned X-rays at the beginning. So what about X-rays? It turns out while we were doing this analysis, some people had the idea to go and take the RAS survey and to stack the X-ray signal around the same SDSS galaxies as the Planck team, and using similar mass bins. And what they find is a significantly steeper than self-similar scaling between the X-ray luminosity in the softband in the y-axis and the mass. And what they conclude is that in order to reconcile this and the Planck result, you need a gas distribution which gets more extended with a decreasing mass, and that's exactly what we found. And when you also compare, you find that their results agrees better with AGN feedback. So that's the cautionary tale I wanted to tell you today. Be careful. And here we were not dealing with, so to speak, black box. We knew what we were doing. So, and with that, I leave you with my conclusions, and I thank you very much.
Thank you, Amandine. Questions for Amandine? No questions here live. So are there anything on Zoom?
Question. Yeah. All right. Yeah. Thank you for the talk. So I have a question about. I mean, given that your analysis showed that you do have to make these like with like comparisons. Do you think that this also gives you more confidence in the AGN feedback prescription, or do you think that there's a chance that with I don't know, more advanced or updated AGN feedback recipes that you would sort of overcompensate or cause or envision any other problems happening?
It does give us confidence that the AGN feedback is indeed what is needed. But as far as knowing exactly how much of it you should put, and I don't think that the Planck data is enough. You need things that work both on gas and on galaxies, and that's not necessarily the same combinations of parameters that are going to do that, give you that. Actually, AGN feedback, the intensity of it doesn't matter too much in terms of the properties of the galaxies. You just need to put some of it. Whereas on the gas, it has a huge impact. So yes, no, I don't think, of course, like comparison are extremely important, and that's the best way to compare models and observation on an equal footing and draw a reliable conclusion. But that the fact that the data agrees roughly with our model doesn't mean our model is the final truth. Of course not.
Got it. Yeah. Thank you very much.
Thank you again. Oh, sorry. We have another question on. Can you press your button on the chair?
Okay, so, and following up on that last note, Amandine, I'm wondering if the end result here, which is quite satisfying, that things seem to fit together when you update the pressure profile, is something that we should have anticipated. Essentially, did the AGN feedback models also predict this kind of non-uniform pressure profile, and we just didn't communicate from one subfield of astrophysics to another? Or is this a lack of predictiveness?
That's pretty much it.
Okay.
If people had looked in simulations that were not no longer non-radiative, they would have seen it. Especially if they had looked at other things than clusters. Of course, if they only look at clusters, they would not have seen as much, but they would have already seen that it flattens out outside of R500, which is also something that Planck found in the ESZ signal. It doesn't continue to follow Arno all the way out to 5R500, which was something that no one expected at the time, even for massive clusters.
Okay, thank you.
Something again. And our next speaker is Shivam Pandey. He's going to tell us about feedback with SED and correlation.
Thanks a lot. Hello, everyone. So I'll be talking about understanding the impact of feedback on the matter distribution, and we'll try to use some other probe to see if we can calibrate the impact of feedback on matter distribution. So the idea being that you would want to add multiple probes that are impacted by the same underlying physics so that you can actually know that that's the feedback prescription that's affecting our universe. So, and also the impact on matter distribution is the leading systematics in most of the weak lensing surveys. So we also want to calibrate it because of that reason. So the work has been done by an master student in University of Hawaii who is currently applying to PhD program, and Eric Baxter. So for this thing, we use the camel simulation. And these are really great because they provide us in the same box, like they will vary all the feedback prescriptions, the initial random seeds, the cosmology, etc. So you can actually try to make a robust model of how any of the observable is impacted by most of the underlying astrophysical phenomena. So for example, in here, you can see that if you take a no feedback box and you try to see what the gas pressure, the electron pressure, and the electron distribution and the dark matter distribution looks like. And as soon as you, for example, in here, start the AGN feedback, you see this thing has way more electrons in the outskirts. The pressure is very, very different. And also the dark matter distribution is a little bit impacted, particularly in the core. So camels is great because they vary all of the feedback parameter that control the supernovae as well as the AGN, in addition to cosmology. So you can, I don't know why the resolution is so bad, but anyway, so in here, if you try to, for example, take all these simulations and try to see what the impact on the total matter distribution is. So in here, it's plotted as the residual to the power spectra, so this delta P over P, as a function of scales. And the different bands that you see are different simulations from camels that vary the hydrodynamical prescription, so TNG, Simba, and Astrid. And all of these simulations like currently fix all the parameter, only the initial random seed is changing. So these are the cosmic variance sims, and you can see the impact is very, very different. And then the light blue panel in here that you can barely see is changing all the other astrophysical parameters as well. And you can see in the TNG, and you can see that relative to the dark blue, the error bar in light blue is pretty large. So that's saying like, yeah, there is a fairly large theoretical uncertainty in how the feedback impacts the small scale matter distribution. So to calibrate this impact on the matter distribution, there was a pretty nice paper a few years back that tried to see if there is any correlation of this matter power suppression with any astrophysical parameter. In here, they focused on the amount of baryons within some characteristic radius, so FP within R500C. And what's plotted is this power suppression relative to FP at a particular scale, and FP is measured at halos and some particular halo mass range. And you can see that this power suppression follows a very tight relation for most of the hydrodynamical simulations. So these vary the amount of feedback and how exactly it's implemented quite a bit. So it's saying that there is some astrophysical parameter that you can use to see its impact on the total matter distribution. And you can maybe understand the shape as well fairly easily, because in here, if the FP is fairly low relative to the cosmic baryon fraction, this is the high feedback regime. And that's the regime where you would expect the power to be mostly suppressed as well. So the shape like intuitively makes sense. But the issue comes that FP is actually fairly challenging to measure. Like to measure it, you either need to do X-ray, which will only give you higher halo masses, or and at lower redshift, or you will have to do KSC studies, which are fairly low signal to noise. But another probe that is also sensitive to gas thermodynamics, but is significantly easier to measure is thermal SZ. So basically, as Amandine said, thermal SZ is as the microwave photon travels to us, it gets upscattered by the hot gas and with a characteristic change in its energy, and we can use it to probe the integrated pressure along the line of sight. So we'd like to see if this probe is also a good tracer of the power suppression. So in here, what's plotted on this panel is again the delta P over P as a function of FP. So this is similar plot that you saw, but now for the camel simulation in some halo mass range. And you can again see there is some relatively tight scatter, even though relative to the Vandalian et al. Plot, it's a little bit more uncertainty. But crucially, on the left-hand plot, you can see a similar thing plotted relative to the integrated SZ within R500C. And you can see these two plots look fairly similar. So again, saying that not just FP, Y also carries some information about delta P over P. So you can try to see that, I mean, this whole plot was just for one hydrodynamical prescription, illustrious TNG, but you can try to see how does this look for different hydrodynamical prescription as well. So again, apologies for the low resolution. But basically, just to say, the right panel that you're seeing is again the higher halo mass is higher halo masses, and different rows are different hydrodynamical prescriptions. So here TNG, Simba, and Astrid. And so this is the plot that you previously saw, but you can see that for the same halo masses, Simba and Astrid also have similarly tight relation, although for Simba it's more uncertain. And in the third column is again like using the Y500 for similar things. So you can see that both of these show similar tight relation in delta P over P and the astrophysical quantity. And on the left two panels are the lower halo masses. So these were 10 to power 13 to 10 to power 14, and then in here 5 10 to power 12 to 10 to power 13. So you can see if you go to lower halo masses, you do increase your uncertainty, but there's still some information that if you can make a robust model as we can from the simulation, you can use it. Okay. Another question that might come is, how does this relation look for different scales? So in here, again, it's the delta P over P as a function of, for example, in here FP, but the story remains same if you change it to Y as well. And you're going from fairly large scale of K of 0.6 to fairly small scale of K of 10. And you can see there is a tight relation remains between these two quantities for different scales. And there is a dashed line that is a very simple model that we show in the paper that you can like intuitively come up with based on like at what scales you are looking the power suppression. So that would impact like how much gas is impacted at how much gas is ejected at that particular scales. And as you go to smaller scales, the relation becomes linear. So basically, the thing is, how do we actually now go from these SZ signal measurements to the power suppression? So we train a very simple random forest model where the input is the integrated by signal, and we try to predict the delta P over P. And the model is trained and tested on all the three hydrodynamical prescription, TNG, Simba, and Astrid. And basically, the result is here. So in here, you can see it's on the test simulation. So what's plotted is the error in the recovered delta P over P relative to the cosmic variance error. So the 1 sigma in here, that is the gray band, shows like the best you can do with any observable. And keep in mind that the error due to the full variation in the whole, say, the Latin hypercube, where you vary all the astrophysical parameter as well, will be fairly large. So you can see that if you now input any of the quantities, either the integrated as the signal or the full pressure profile you do recover the delta P over P to similar range, to similar precision as the cosmic variance sims. So this is saying that the model is robust enough, particularly on small scales, to give us a pretty good model of delta P over P, of course, given the underlying simulations. So in here we have used 3 simulations, and in future, like as CamelSats, more hydrodynamical prescription, Ramses, or Magneticom, we will try to use those as well. Okay, so we would like to see if we can already connect with data. So few years back, we did this analysis where we tried to analyze the correlation between the weak lensing and the TSZ signal. So particularly taking the weak lensing map from DES and the TSZ map from ACT. And we correlated, so both ACT and Planck, and we correlated these in various tomographic bends. So what you see here is this correlation between weak lensing and TSZ as a function of angular scales for various different tomographic bends going from low redshift to high redshift. And basically, it was a pretty high statistical detection. It was pretty high statistical detection of the signal at 20 sigma, and we came up with an analytical model to get the fit. So basically, you can imagine writing the shear cross y as one in the halo model prescription as 1 halo plus 2 halo. There is a systematic contribution from the intrinsic alignment of the source galaxies correlated with SD. But basically, you can boil it down into it's a function of pressure profile, a function of the dark matter profile, and some function of cosmology. So the cosmology is fixed to either Planck or DS values. The dark matter profile we provide full freedom, and the pressure profile we parameterize it as a GNFW parameter with 4 free parameters. So, and this also has its mass and redshift dependence that Amandine was pointing out that is required to get a good fit. So basically, we get the fits to these pressure profile parameters, and then what you can do is you can take these fits and try to infer what the 3D pressure profile actually looks like. So that's the plot on the right. So this is, for example, the 3D pressure profile as a function of R inferred from these constraints. So basically, the bands here correctly fold in all the measurement and modeling uncertainties, and you can then start to compare with different simulation. So basically, what we do is, from what you saw in here, we have trained a model where you can give it either a 3D pressure profile or an integrated SD signal, and you can try to recover what the matter power suppression is. So basically, we take these 3D pressure profile and try to infer what the matter power suppression is, and those are the black points. So in here, the black points take those 3D measurement and infer the suppression as a function of scale. And we compare that to either the OWL simulation that you just saw or to Bahamas and TNG simulation. And it does seem like even from this probe, the OWL simulation seem to perform pretty well. And it also agrees pretty well with all the future, all the previous studies as well. And just to point out, like, we also see how well you can do in future using some DESI like, say, group catalog and CMBS4 like SD catalog. And you can see in blue, the error bar get pretty tight. So in the sense saying that if we can reduce the uncertainty in the pressure profile, and particularly in the halo mass range we probed here, you can get huge gains in the matter power suppression. So yeah, that's it. That I mean, just to conclude that there does exist some tight relationship between delta P over P and SD, and the relationship that was in Vendalen et al. Does generalize to other feedback model, although with a larger spread, and we can already use the data to constrain the impact on the matter power suppression. And just to mention that in the paper, we also explore if we can get the bispectra suppression as well, which does seem to work with some caveats. So yeah, I mean, please check out the paper. Thanks a lot.
Really interesting. I'm not an expert in this field, and I wanted to ask you, in the plot where you showed the errors relative to cosmic variance, could you, are you doing too well? Like, should you expect more of the points to be outside of the band, like maybe 1, because it's 1 sigma?
I mean, so cosmic variance error, if it were better than cosmic variance error, then I would say we're doing too well. But if it is like at least a little bit bigger than cosmic variance error, I mean, I guess that's expected, right?
So you expect the error bars to be exactly sort of what?
Yeah, I mean, if it should not be better than the cosmic variance error, so it should not be better than 1 sigma.
You don't expect any points to be outside that.
Oh no, because I mean the bias should be reduced, right?
Okay.
Like the bias should be close to 0. Yeah.
Okay.
So
that's
yeah, also in here we are plotting the mode of the PDF. Like we get the full PDF, and what's plotted is the 16th and 84th percentile relative to the mode. So yeah, so the PDF is a little bit skewed sometimes. So that's why you see some points that scatter differently.
Very nice. So now I've understood you are training on all these models and try to infer, the properties and observations. I was wondering if, since all these models have different feedback prescriptions, if you can do some kind of SBI or something like that to try to constrain the feedback instead of, using them jointly but separately, and try to, constrain what would be the feedback models that are more compatible with observations.
So you mean like fold in more observations?
Sorry?
Are you saying like fold in more observations? And
I mean, and using models separately as different, realizations of feedback models, and then use these to compare to observations and get some contour plots or something like that about some confidence values of what are the feedback models that are more compatible with observed data.
So the only issue I can think of is the way you would parameterize what the feedback is. Like as you're saying, like on what parameter are you going to make the contour plot? Just because the parameters that these different simulations vary mean more or less very different things in different simulation. So you cannot just get the constraints on the parameters as is. So you would probably have to either go to some observable, or like try to extract a common metric of feedback from all the simulation. But yeah, I agree, like if you can do that, that'll be a very interesting thing to do. Yeah.
Yeah, so I have a question about scales, because the camels boxes are fairly small. So you train you train your model basically on relatively small boxes that don't have very massive halos and no clusters basically.
Yeah.
And then your final comparison was to bigger simulations. But how do you trust your model in that case?
Yeah, exactly. So I mean, that was a very big worry, and we did try to do the validation on this matter power suppression using larger TNG boxes. And we do find that there is some dependence on the resolution, less so on the box size. So camels also has a little bit lower resolution, but even though in here you can see the matter power suppression from camels in different bands, 1, 2, and 3 sigma, and from bigger TNG boxes. So it's like at approximately 1.5 or 2 sigma deviant. But so, and that was the thing that I was saying, that bispectra, even though it works for bispectra, we cannot trust that because bispectra is very sensitive to box sizes. So in there, we don't do any comparison with data. We just say that in future, if you have bigger simulation, you can do it. But for power spectra, it seems the box sizes are decent. Yeah. Thank you.
Thanks, Shivam. Our next speaker is Yongseok, talking about cosmological parameter estimation.
Hi. Hi, I'm Yongseok Jo. I'm a postdoc at Flatiron, and today I'll be talking about model sensitive estimation using cosmological simulation. What I mean by model sensitive is if you think about like just conventional estimation tools, then we usually trained a network or some machine on just one same kind of simulations and make predictions on the same simulations. Then we'll have this type of like parallel like scheme. So the estimator A, B, and C are not compatible with each other. But what I'm trying to do is build a like model sensitive, insensitive estimator that can estimate a parameter from like regardless of what models I choose. Like these, the models I'm talking about here is could be like TNG and Simba, like Astrid, as Shivam mentioned, like in terms of like camels project. So what I like to have is like model insensitive estimator that can give us like consistent prediction out of different types of simulations. And if you take a look at some simulations, so as I mentioned, we're currently like thinking of camel simulations, which consist of TNG, Simba, Astrid, like Mechanicum, some others, but mainly Simba, TNG, and Astrid here. So they're actually very calibrated in terms of like stellar mass function usually. So the stellar mass functions are quite in a good agreement with each other. So these are from like different papers. They're on paper, and it looks very quite similar in terms of like the observations are very similar. If I overlap all three figures, then you'll see they're very on top of each other. And ratio of 0 also, they're very similar. They are calibrated well against like observations. But as Shivam mentioned in this talk, there's difference in especially in small scales. So if you take a look at the total density map here, so it looks very similar in terms of like large scale. But if you take a look at some like details, then you'll see quite significant difference. So if I train the neural network on one simulation and apply to other, then they won't work well, I guess. And this is some short movie that the two images are like alternating here. You can see some differences. And um, this is getting worse if you take a look at variance only. This is H1 map, the H1 density map at redshift 0. And you can see like significant difference in gas properties or like stellar properties. So yeah, you can see. So how I trained we build a machine to kind of like suppress the uncertainties from these like baryon physics or the subgroup models. So this is our neural network, which consists of like encoder and classifier and some regressors. So the point of this our neural network is there's three goals. So in encoder, we're trying to compress the simulation data into like some latent variables here, Z, which is you could think of it as the summary statistics. And there's also classifier. So we use classifier to like declassify the simulations, which means to like get rid of some informations about like models. So the latent variables, we like to latent variables have like nothing about like models. And regressors, of course, they're for regressor. I mean estimation, primary estimation, the usual. And this is our loss function. So we have like mainly three loss functions: the regressors, J1 and J2 here for regressor, and H is cross entropy for classifier, and here I is mutual information. So mutual information between simulation data and the parameters. So here we're trying to like minimize the cross entropy and mutual information. Oh, I'm sorry. So mutual information here is actually latent variables and a simulation. So if I reduce the mutual information of latent variables, which is summary statistics and simulations, that means we're trying to compress the information. So we're trying to minimize the visual information, and to declassify, we minimize the cross entropy, and for the accuracy of the estimation, we're trying to maximize the MSE, like the J1 and J2. And there's two training phase. This is very similar to GAN, like adversarial training. So first phase is train classifier first, without training any other parts like encoder and regressor. So we try to have like good classifier here first. Then in phase two, we're going to train the machine without classifier. So we're good with the classifier now. So we're trying to train other parts like encoder and regressors, so that they can be like compress and do some declassification like procedure like that. Oh yeah, yeah, every epoch and iteration we do it all this. Yeah. And I'll show you some results. So this is machine prediction trained on TNG and Simba, and separately tested on TNG and Simba in a test set. So you can see like they look very good, and the relative errors of omega aim and sigma 8 is very small, like 5 and 4%, which is good, and without negligible like biases, I guess. So which is very good. And we did this on also with H1 map. Yeah, H1 density map. And also here, they look quite well, except that here there's some like scatter, but still I think it's okay, given that this is just Boolean map. So, and relative error and bias is a little bit increased compared to the total density map, but still I think we can do something or to suppress the bias. And also we did it with 3 different simulations, TNG, Simba, S-Street at the same time. And these are separate. We tested on each simulation here. And also we are kind of successfully predict the cosmological parameters without bias and with good accuracy of estimation. Also for H1 density map. But what we're actually trying to do is train a neural network that can predict cosmological parameters from the simulation or observation that the machine has never seen. So that's we did next. So we trained on machine on Simba and TNG and tested on the S-Street with total density map. I think this is not that bad, especially in terms of like sigma 8. There is some scatter, obviously, but not that bad, I guess. But here you can see some biases, like in omega m. This is something we have to like more optimize or figure out how to suppress the bias. Maybe having more simulations would be better solution here. And we also did it with H1 density map, but the results are not that good compared to the previous total density map, which is, I think, kind of because it's just baryons without any like dark matter features. So this is kind of obvious, but I think we can maybe in the future we can come up with some solutions to address this problem. So yeah, here sigma 8 is not good. Omega m, there's some bias, but the global, I mean, trend is very similar. So, which is promising, I guess. Yeah, we are trying to build a model sensitive estimator that aims at like suppressing the uncertainties from the like model, so selection of model, choice of model. And we used like a GAN-like training procedure, and we did good we made a good prediction with without any biases, but we still things to figure out with the test part, application part. Yeah, thank you.
Questions for Yongseok?
Thanks very much. This is very nice. In fact, you're doing adversarial domain adaptation in some sense. So this is basically something which is used a lot in natural imaging or other applications.
Mm-hmm.
But in some sense, people, what they usually do is, they show some label sample. In that case, would be one simulation. And during training, you will show data from the other simulation that you want to apply with, but without any labels. So just, trying to make that the summary statistics overlap, even without labels. In your case, you are, trying to do it, let's say, maybe harder in the sense that you're training with several simulations and training the regressors on these simulations. So you're using labels for all of them. And then you go to another simulation for which you've never shown anything. And so this, makes it harder. So I wonder why you are not doing the standard domain adaptation approach, which would be, you show, in that case, images of Astrid, but you don't say what is the ground truth for Astrid. You just show images so that the latent variables overlap. And so this is something that you could do eventually with observations as well, because you don't need ground truths.
I'm not sure if I follow you perfectly, but so actually we're not using just actually the raw simulation data. We used some summary statistics out of some compressed inputs, which is we used scatter transform, like wavelet transform, to compress the simulation like first. But using those type of summary statistics, it is a little bit hard to have like common statistics that can be like applicable to any simulations. I don't think I'm making any sense, but yeah.
Yeah, but anyway, we can discuss later. It's just the way, I think I understand, but it's the way you train that anyway, we can discuss later, no problem. Okay.
So the plot where comparing to Astrid again. So, in some sense, you might expect some biases and so on to appear, but the fact that you've gone to the trouble to put error bars on all the points makes me think one of the reasons you did that was so that at least your error bars would have blown up if everything were working, and it would have said, well, I don't know, but it's consistent. And instead it says, I know, and it's wrong.
Yeah.
Yeah.
Yeah. So
is there something, I'm just wondering, if there's something about the construction of those error bars? We were talking about epistemic uncertainties yesterday, right, in the tutorial, and it seems like that's what you're trying to get at and somehow didn't.
Yeah. So these error bars are actually from like training data, so not from like multiple trials or something like that. So I'm not sure how the correct interpretation of this error bar here. Yeah, I think I have to think about that more.
I was wondering if all these simulations have similar spatial resolutions, or if you're losing any data by needing to like have them all be the same input size. I guess, how are you inputting data into your network across the simulations?
Sorry, I think I follow you.
So like when you're inputting data from all of these simulations as your input, do they have the same resolution, or do you have to lose resolution in any of them?
Oh no, they're they're similar, same. They're very much same resolution, and like they are somehow like calibrated. This is camel simulations. So yeah, can say that. Yeah, they're.
So the shape that you see with the astrid plot of this kind of like going up and then like down again, yeah, even in the one you had before, where you kind of have this like convex shape of compared to the diagonal line. You do have that a little bit already in both GNG and Simba. Like you can see like the same trend being there. It's just magnified. Why do you have that trend in CNG and Simba where it's biased for both high omega m and for high sigma 8?
So
like it's a somewhat peculiar shape. It's not like it's completely symmetric. It's
right. What are you raising?
Okay, sure, yeah.
Yeah. So yeah, I've definitely seen this weird trend. Like, so if I do the linear regression with my data without any like proper optimization, then I'm gonna have this type of curve. But yeah, I haven't really carefully looked at why that happens. So yeah, but that kind of behavior is pretty much the like common across different simulations. So yeah, I think I have to take a look.
I think this is typically an artifact of the main mean square error loss. By definition, the mean square error loss is optimizing the mean of the posterior distribution. And so at the limits of the edge, at the edge of the distribution, it will tend to go towards the mean of the distribution because you cannot go beyond that. So it's it's the way you build the loss function that makes sense.
Like yes, that's a configuration, except that that's not what it's doing. Like it goes above the mean, like here in the middle. Like so. Sorry. Okay. Yeah. Okay. I'll come back to you about it afterwards.
Discussion session. So let's thank Yongseok again. Now we will move to our last speaker, who is online, Naomi Gluck.
Hello, I will just share my screen and okay.
Whenever you're ready.
Thank you. So today I'll be talking about deep learning the circumgalactic medium at CGM, take 1. So this is pretty much the first time that we're using what we're calling halocentric data within a neural network to predict or to infer properties of the CGM. So the science goals in the bigger picture, what do we want to do? So we want to infer, again, underlying CGM properties from input maps. And maps are in quotation because they're not really maps, they're discrete data points. So the map that you see on the right really does come from just discrete data points, and it's filled in. A lot of these values are actually 0, but to get a more physical picture, we've just said that 0 will be equal to the minimum value within this discrete data set. So we're doing this specifically for H1 and X-ray for the time being. And so H1 traces cool gas around 10 to the 4 Kelvin, and X-ray traces hot gas with a temperature greater than 10 to the 6 Kelvin. And so we also want to compare the precision and accuracy of multiple simulations. Right now, we're just focusing on illustrious DNG, but definitely hope to get in Simba and Astrid and really make the network as flexible as possible so it can take in any simulation as a training input set. And so we want to do this to obtain optimal telescope or multi-wavelength survey conditions for CGM analysis, and then evaluate how these different telescopes and surveys measure the CGM. So the runs that we have currently been working with come from the light version of this neural network. So there are two versions. One is available on Google Colab, and there's then a full version, which we have just started to work with. Definitely needs a lot more tweaking. So all of the subsequent plots that you're going to see are from the light version of the neural network, which honestly doesn't do that bad of a job, all things considered. So we're looking at idealized H1 mapping, X-ray mapping, and then combining those two together. Then we're now introducing observational limits for H1 radio mapping, observationally limiting X-ray mapping based on the Erosita all-sky survey limits. And then we're combining those for an observationally limited H1 and X-ray prediction or inference on the parameters that we'll get to on the next slide. And just some technical things for the full run, or the full version of this neural network. You need more than 10 trials to get improvement with around 200 epochs per trial. And this number is not random. It's the number of trials that will get you past this random trial phase. And after 10, you'll really start to get a lot of learning that the network does. And we obviously still need to do some additional tweaks to the network, but we're very close to getting it fully up and running. So the 6 parameters that we are looking at is first the log of the mass of the halo, so the total halo virial radius within R200 as kind of an offshoot of the subsequent 5 parameters. Then we're looking at the log of the mass of the CGM, so mass of the CGM within 200 kiloparsecs. Fcool, the fraction of the CGM mass within, or that is less than 10 to the 6 Kelvin, also within 200 kiloparsecs. Then the log of the temperature of the CGM and the log of the metallicity of the CGM, also both of these within 200 kiloparsecs. And finally, FCGM as the mass ratio of CGM gas to the total mass inside R200C. And so this can be approximated as mCGM over m halo, and I think that should be reversed. So I apologize for that. And essentially these are field-dependent network outputs, which will give us our inference and truth plots, which we'll get to in a moment. And so here are some of the initial results. Looking first at the H1 idealized, we have Fcool on the left, log of the temperature in the middle, and log of the metallicity on the right, and the colors correspond to the mass of the halo. So the purple is for the lightest mass, 10 to the 11.5 solar masses, going all the way up to yellow, which is 10 to the 14 solar masses. And so Fcool and log of the temperature have, well, sort of trends. Fcool is not really constrained as the points themselves, which by the way represent 1 halo per point. They're quite spread from the y equals x black line, and the log of the temperature does pretty well. However, for the metallicity, it's really not clear at all what's going on. So H1 alone is not enough to give any conclusive results on the metallicity of the CGM. And our hope with combining not just X-ray, but different lines is that maybe one combination of these lines will be able to constrain really well any of these 6 properties. Now moving on to FCGM, MCGM, and mHalo, again with the same color bar scheme. mHalo has a really, really nice monotonic trend. And MCGM, not so much. FCGM is kind of all over the place, both not by having a monotonic trend and that the points are quite spread from the y equals x black line. And there might be two reasons for this. One is that, well, for the spread, I sort of think that there's an inference overlapping going on, where if FCGM is related to both mHalo and MCGM, and we're also testing and training for those two properties, that there might be some sort of bleed between what the network is inferencing over. And also, unique to illustrious TNG, it has a dual mode AGN feedback, where there is a mass cutoff between going from quasar mode to jet mode feedback. And so that might lead to this flipped FCGM trend, but definitely can talk more about that later. But I thought that was just an interesting thing to point out. And so now we are combining H1 with X-ray, and I'm not going to show all of the parameters, but just, most improved. So a lot of the temperature with the right plot is just H1, and it's already pretty good. And now we're introducing X-ray. So it's, I think, helping in the low mass range particularly. And so the constraints are definitely improving. And so this is a good sign that the network, even the light version of the network, is doing what it's supposed to do. And so now we're looking at fcool, where on the right we have H1 only, and then on the left is H1 plus X-ray. And so you can see that all of the points have kind of moved closer together, surrounding the y equals x line. And so the other parameters that I haven't shown basically remain consistently good or bad with the addition of X-ray. So I'm not going to show them in the interest of time, but that's basically the full story when we're adding X-ray. Now going on to, well, what happens when the Euroceta observational limits are taken into account? And so the large plots here are a combination of X-ray and H1, and the two small plots are H1 separately and X-ray separately. So the collection of plots on the left deal with MCGM, and on the right, mHalo. And so you can see that on the X-ray plots, which are boxed out in red, in the low mass range, something weird is going on, and this is what we expect, that it's not so great when we include these Euroceta observational constraints. However, with the addition of H1, it helps significantly. I think that's pretty clear here, especially in the low mass end. And so this points to the question of, can we use machine learning and neural networks for observational proposals, since we'll be able to say, okay, maybe look at something instead of something else, and to kind of facilitate the process of choosing what to observe and what will get the best results in the end. So a few summary and discussion points, mostly discussion points, kind of pointing towards which observational surveys to keep an eye on, and why we've chosen, I guess, certain binnings or certain simulations. So looking at the CGM, where specifically for less than 10 to the 13 mass solar mass halos, there are a few constraints on the total gas, other than the fact that the interiors of these halos are completely devoid of their cosmic abundance of baryons. So the handful of X-ray halos that are observed may be abnormally bright, and so Euroceta, as kind of something that we can ground to in terms of observational results, will help constrain this, but we obviously can't calibrate to any observations just yet. Looking at group mass, so low mass groups are 10 to the 13 to 13.5 solar mass halos, where there are only very few in looking at the 1P set. So 1P meaning changing one parameter at a time in the camels set specifically. So still there are very few observed in X-ray, and so we might look to SC for more compelling initial results. for high mass, going from 10 to the 13.5 to 14 solar mass halos. There are also significantly devoid of baryons. And since the X-ray profiles can extend to around R500, we can calibrate to the slope and fitting with the halo baryon fraction to this. And so we can get more data from XMM group surveys. However, this might induce some possible X-ray selection bias. And also, again, the ERC to all sky surveys. Now with simulations, the first two that we're definitely going after are Luster CG, which you've seen here, and Simba, which we hope to get to next. And so there are differences in the astrophysical feedback. So they have different halo mass and assembly times. And so that definitely leads to differences in inference versus truth plots. Both are calibrated to group gas fractions, but have diverging profiles. So this will be definitely an interesting aspect to delve further into. And also just in general for how I'd like to continue building and changing the network so that it is flexible enough to include other simulations like Astrid, Eagle, and anything else. So I guess as a summary statement, that neural networks can really help solidify constraints and pinpoint future observational necessities in terms of what we need to look for in order to find robust scientific results.
Questions for Naomi?
So I think it makes sense that you can predict what observations will be useful with this method, certainly well enough to motivate writing telescope proposals and the like. But if you really want to know if those are going to bear fruit, like say you want to design it as a PhD thesis project for a student, how can we be sure of that since you're using the correlations in the simulations? Is there any way to try to figure out ahead of time if those correlations will exist in the observations themselves?
So I think that kind of goes hand in hand. I think eventually, once we are confident that the full version, and full version is really key here because everything that you've seen is from the light version of this neural network. And so the full version will be able to say, picking out features of what might be most important to look for. And eventually we'd like to actually feed in observational data into the network and then see how that will compare with the results that we've gotten from simulations. I don't think they're, at least right now, because this is relatively speaking a new project for me. I don't know if there's a way to predict if the outcomes of these simulation inputs are directly going to be something that is currently in an observational survey, but definitely for upcoming and future surveys, we can give proposals and say, well, from simulated data, and obviously we'll have gone through many different simulations and testing and training in combinations of simulations. This is what we found. This is what will produce the best constraints. This is what you should look at. So I think that kind of goes hand in hand. I hope that answered your question.
Okay, thank you.
Question? Not. Let's thank Naomi again.